Have you ever seen a huge car getting lifted in a service station with just a small press of a lever? Ever wondered how such a small effort can lift something so heavy? Well, welcome to the world of hydraulic machines, a brilliant application of pressure and fluid physics. Hydraulic machines use liquids, usually oil or water, to transmit force. And the key principle they rely on is Pascal's law. This law tells us when pressure is applied to a confined liquid, it gets transmitted equally in all directions. So even a small force on a small piston can be used to create a large force on a bigger piston just by manipulating the area. Let's recall the formula. F2 equals open bracket A2 divided by A1 close bracket multiplied by F1. That is, the force on the larger piston equals the ratio of the two piston areas multiplied by the force applied on the smaller piston. Amazing, isn't it? A small push can do big things, literally. Now let's understand how Pascal's law plays out inside these machines. Pascal's law states the pressure exerted at any point of a confined liquid is transmitted equally in all directions. The formula we use is P equals F divided by A, that is, pressure equals force divided by area. In a hydraulic system, you push the smaller piston with some force. This creates a pressure in the fluid. And since pressure is the same throughout the fluid, it acts on the larger piston too, producing a much larger upward force. So, with a clever arrangement of pistons and fluid, you multiply force. Take a look at the diagram here. You see the pressure applied on the small piston traveling through the liquid and pushing the larger piston upward. Let's bring this idea to life with a real-world machine, the hydraulic lift. These are the machines you see in car garages, used to lift heavy vehicles. But here's the magic, they do it using very little effort. Here's how. The mechanic applies force on a small piston using a lever. This generates pressure in the fluid. That pressure then pushes up a much bigger piston, the one carrying the car. Imagine the input piston has an area of 10 square centimeters and the output piston has 100 square centimeters. That's a tenfold increase in area, and hence, the output force will be 10 times the input. That's mechanical advantage in action, all thanks to simple fluid physics. Take a look at the diagram. You'll see how the two pistons are connected via a fluid chamber and how this setup makes lifting heavy things easy. Now let's talk about something you use daily, your car's brake system. When you press the brake pedal, you're actually pushing fluid in a hydraulic system. That pressure gets transmitted through brake lines to all the wheels and stops the car. Here too, Pascal's law is at work. The pressure from your foot is transferred equally through the fluid to the brake shoes at each wheel. So you don't need to be a weightlifter to stop a fast-moving car, just clever fluid mechanics does the job. Let's recall the same formula, P equals F divided by A, and that pressure is distributed evenly to bring your vehicle to a smooth halt. As you can see in the schematic, the master cylinder connected to the brake pedal pushes fluid into slave cylinders, engaging the brakes on each wheel simultaneously. Another amazing device is the hydraulic jack, often used to lift vehicles during tire changes. The jack uses a simple handle that builds pressure in a small oil chamber. That pressure is transferred to a piston that slowly lifts the vehicle. So once again, a small input force applied over time becomes a big output force. Let's do a quick example. Suppose you apply a force of 200 newtons on a piston with a small area. If the output piston is 10 times larger, the output force becomes 2000 newtons. That's enough to lift a small car. That's the power of Pascal's law packaged into a portable tool. Let's now solve a numerical to reinforce what we've learned. Imagine a force of 150 newtons is applied on a small piston of area 0.02 square meters. We are asked to find the force on a larger piston with area 0.4 square meters. Step 1. We calculate pressure on the small piston using P equals F divided by A. So that's 150 divided by 0.02, which gives 7,500 pascals. Step 2. Since pressure remains the same throughout the fluid, we apply it to the larger piston using F equals P multiplied by A. So, 7,500 multiplied by 0.4 gives us 3,000 newtons. That means the output force is 3,000 newtons, all generated from just 150 newtons. Isn't that incredible? Let's quickly recap. Hydraulic machines use Pascal's law to transmit pressure through a liquid, allowing small efforts to produce large outputs. The formula we keep coming back to is F2 equals open bracket A2 divided by A1 close bracket multiplied by F1. It shows how force multiplies when the output piston area is larger than the input. You've seen examples like hydraulic lifts, brakes, and jacks, all using the same principle in different forms. So the next time you're in a car, at a workshop, or even operating a jack, you'll know it's not magic, it's physics in motion. Hope this session gave you a clear insight into the power of pressure in fluids. See you in the next session with more real-world physics.